Hi, I'm Heidi Jauhiainen, and I want to tell you about our ongoing attempts to segment hieroglyphic texts. Now, in order to use digital methods to study texts, the text must, of course, be machine readable. But Egyptology, the study of ancient Egypt, it doesn't have a tradition of publishing machine readable hieroglyphic texts. One of the problems is that the hieroglyphs were written in kind of boxes where signs can be placed above others. And sometimes a sign can even be over another one or nested inside a bigger one. So when Egyptologists study handwritten texts, they transcribe the cursive signs back to hieroglyphs. And this often used to be done by hand because otherwise the proper placing was not possible. But since the 80s, at least, it has been possible to use computers to make the transcription. And for that, specific hieroglyphic text editors are used. These editors use encoding to produce the hieroglyphs. The codes come from a standard reference list where the hieroglyphs are grouped into categories. This encoding represents the signs better than the transliteration, which in Egyptology is already an interpretation of the words. Now, from the hieroglyphic text editors, one exports the hieroglyphic text as a picture, while the encoding is saved in files with the extension GLI. These GLI files are meant for the text editor, and when no compatible program is available, they behave like a binary file. So most of the time, such files have been thrown away without realizing that they contain a machine-readable version of the text. And so not many machine-readable texts have been published. The now available machine-readable hieroglyphic text corpora are based on such encoded texts. The Thesaurus Lingua Egyptia released a snapshot of the database behind their online service in XML format. The texts behind the Ramses online service were published by Serge Rosmelduc after he used them in his attempts to build an automated transliteration software. These Ramses transliteration corpus texts are not annotated at all, and the encoding is not even aligned with the transliteration. In the machine-readable texts for Egyptologists project, the aim is to facilitate the use and production of encoded hieroglyphic texts. We published a tool called GLI to MDC that extracts the encoding from a GLI file and save it in a simple text file. In order to build transliteration models of both available corpora, we also devised a method to align the Ramses corpus encoding and transliteration sentences. One of our aims is to build an automated transliteration method, but the first thing one must do is to segment the text into words, since hieroglyphic texts do not indicate words or sentence boundaries. To train our segmentation method, we use the Ramses transliteration corpus training set, which has a version of the sentences where word boundaries are indicated. And for testing, we use the validation set. As a starting point, we used Homburg and Chiarcos's report on their attempts on segmenting Akkadian cuneiform texts. In their experience, the dictionary-based methods worked better than rule-based methods or machine learning algorithms. To measure the correctness of the automatic segmentation, we use the word F-score, which is one of the measures used also by Homburg and Chiarcos. The word F-score combines word recall and word precision. Word recall is the percentage of correctly segmented words out of all the manually segmented words in the validation set. And word precision is the percentage of correctly segmented words out of all words produced by the automatic segmentation. The best word F-score for Homburg and Chiarcos was 65.05, which was attained using the maximum matching algorithm, which is also known as the greedy algorithm. And we started by implementing it using all the encoded words from our transliteration models as a list of possible words. This method that looks for the longest possible words achieved an F-score of 61.62 for the hieroglyphic text, which is reasonably close to the result attained by Homburg and Chiarcos for cuneiform. The most obvious problem with the greedy algorithm is the fact that when a long word is not in the dictionary, the word is divided into many short ones, as can be seen in the example here, where the algorithm has incorrectly divided one word consisting of 9 hieroglyphs into 5 short ones. And hieroglyphic words can be written in various ways using many different combinations of signs. And this makes it more likely for the word form not to be found in the word list. Then we decided to try a rule-based method and implemented the prefix-suffix method from Homburg and Chiarcos. The method compares the probabilities of a sign being at the beginning, middle, or the end of a word, or as a single character forming the whole word. With the F-score of 35.83, the method worked better on hieroglyphic text than on cuneiform, but far behind the greedy algorithm. Now, hieroglyphic words often end in classifier signs that help the reader tell apart the words with the same consonant root. The words here were probably pronounced differently, but only the consonants can be deduced from the writing. Hieroglyphic classifiers can also have phonetic value and be used alone or in some other part of the word. Like the circle here depicting the sun that tells the word is day, it can represent the word by itself with a stroke. So the place of a sign within words is not constant. We did nevertheless make our own version of the prefix-suffix method, which looks in between characters and compares the frequencies of having or not having a boundary after a character and before the next character. Since some signs are much more common than others, we used relative frequencies. This method worked better than our implementation of Homburg and Chiarcos' prefix-suffix method. Next, we compared frequencies of break and non-break between two characters. This worked well with this kind of text, better than the best method for Akkadian cuneiform. Four-gram method obviously did not work as well as bigrams, but we then added a back-off scheme that reverts to our bigram and unigram methods when the pattern is not in the training set. And now the word F-score grew to 86.54. Starting from 6 grams and backing off to 4 grams and so on, increase the word F-score only slightly more. Our back-off method works fairly well, but one must remember that our test set was in domain. Since we plan to use segmentation as a pre-processing step before automated transliteration, we need a much better method. Although we are skeptical because of the small size of our training data, we are planning to test deep learning methods that have recently been successfully used on Akkadian cuneiform texts by another team. But as we have seen, Akkadian cuneiform is very different. So if anyone has any suggestions on what method might work with this kind of text, we would love to hear. Thank you.